All right, so we're starting on 5.4, the fundamental theorem of calculus. The fundamental theorem of calculus connects integration and differentiation. We've talked about this a little bit. I've mentioned it a few times, but we haven't actually done it. Enabling us to compute integrals by using antiderivatives of the integrand function rather than taking limits of Riemann sums as we did earlier. So first thing we're going to look at is the mean value theorem for definite integrals. Basically, this theorem states that if function f is a continuous, it's a continuous function on a, b, then at some point in a, b, there exists essentially a value, f of c, such that it equals the average value of the function on a to b. Think of it this way. If you get on a highway that has a speed limit of 60 miles per hour, all right? And let's say it's a toll road. So you get on and you get on this toll road at 12 noon and you drive 120 miles and you get off at 1:30 p.m., right? And a cop pulls you over then immediately after you check out with the timestamp and says, you drove that in an hour and a half. It should have taken you 2 hours. I know you were speeding. And then he proceeds to write you a ticket for what your average speed was during that time. The reason he can do this is not because he saw you going that speed, and it's not because you went that speed the whole time, but it's because at least at some point during that trip, you might have been lower than that speed, your average speed. You might have been higher than it at other times, but you had to have gone that speed, right? It's kind of like if I said, take a look at this, let's say we had a graph and I said, here's this point and here's this point. And then we're going to make this infinite line right here, okay? I want you to draw a point from point A to point B without lifting your pencil and pretend that line with the arrows keeps going forever without ever crossing that line. Can you do it? No. And that's essentially, if we drew that line, that infinite line at the average, it'd be impossible to get from one to the other without crossing it. So at some point, you must have gone that average. In fact, there was a place that did give people tickets like that. If you traveled up through the toll road too fast, they'd pull you over, they'd give you a ticket for your average speed if it was too fast. So speed, I guess, get there at 1:30, pull over to the side of the road right before the toll road, get out, eat some lunch, go on through at 2 o'clock, you know. Right? Okay, so that's what our mean value theorem states. It's basically saying we have to at some point get there, and that's what you see in this picture. We are crossing that average height, okay? The average can't be above. In other words, average has to be between the start and the minimum, right? It can't be somewhere there. So you have to cross it. Even if you started here and went up and ended here, you crossed the average twice, right? If that's where your average is, you had to have had it at some point. So does that make sense to y'all? A little bit intuitive, right? Not too bad there. Okay, good. Let's go on then to our next page, where we have the fundamental theorem of calculus, part 1. An antiderivative exists. So what we have here is if function f is continuous on a, b, then capital F of x equals the integral from a to x of f of t dt, and is continuous on a b and differentiable on a b with the parentheses there. And its derivative is f prime of x equals the derivative of the integral of f of t dt and remember essentially what this is equals d dx of f of x kind of a thing. That's just kind of like a little aside, right? That's what we're doing. If we integrate, you don't have to write that last little part in brackets. I'm just writing it for a moment before I erase it. If you look at that part, that's essentially what we're doing, right? That integral of a function of time, where we go from some constant up to x, is going to give us a function of x when we actually do that, because we'll be plugging in a, which is a constant, so it'll just give us constant, but then we plug in x, which is a variable, and so we'll end up with a function of x. That's all I'm saying there, okay? That's what it is. All right, so let's take a look at this. So we're saying f of x equals integral from a to x f of t dt. So how do we differentiate f of x, that big F of x? All right, well, we can use our definition of a derivative. Anybody remember it from back in Calc 1? Good. And then this has to equal some f of x thing, our integrand there, right? Hopefully, yes. All right, so let's take a look at this. If we look at integral a to x plus h of f of t dt minus integral from a to x of f of t dt. That's just the top part. That's our f of x plus h minus our f of x, right? The top part of our limit there. See that? Okay. If we look at just that top part, so we're looking at, we're looking at this right here. Okay. All right, so we're looking at that. This is going to equal what? Well, we have our, let me move this left some because I'm going off the page. This can equal, right, using our limit rules, this is equal to what? I can swap that and make it from x to a and make it plus, right? And then it's, or swap the first one or whatever, and then I can make it from like x to a and a to x and all that stuff. And anyway, ultimately, using those things, swapping our limits around, we get x to x plus h f of t dt. Okay? Then we look at this. We're going to have by mean value theorem, which we just did, we've got 1 over x plus h minus x times our integral x to x plus h f of t dt, right? That's just the average, isn't it? X plus h, and x plus h is b, and then the other is a, right? 1 over b minus a. That's what we have there in that first little part. So that's our average. And that's just going to equal the average value f of c. Well, yeah, by that mean value theorem. Okay, so this is essentially what we have here. We've got f of x plus h minus f of x, kind of bringing it back together, over h is our f of c. And now, if we take that limit as h goes to 0, c is essentially going to get pulled right to x. So if you think about this, if we're looking at point x, and then we're moving over to some point x plus h, right? So we were at x, and we're moving over here to x plus h. So as h goes to 0, right? In other words, as we push this h toward here, right? So if they're this far apart, our average is like here, right? But if we move h to here, our average goes to down here or something like that, right? And as we keep pushing h closer to 0, in other words, we're pushing our point closer and closer to x, where does the average value go to? X. Because x plus h goes to h. We end up getting, essentially pushing x plus h to x, and it's like the average of, what's the average of 8 and 8? It's 8, right? So so as h goes to 0, c is pushed to x. Does that make sense? Therefore, the limit as h goes to 0 of f of x plus h minus f of x over h equals f of x. Therefore, f prime of x equals f of x. That should be pretty cool. We're seeing that right there, that when we take an integral, right, it's the antiderivative. Like a big mathematical coincidence or something, right? You can almost think about it when you're taking a derivative, you're breaking something apart. When you're taking the integration, you're putting it back together. Like, what's the derivative of pi r squared? What's the derivative with respect to r of pi r squared? 2 pi r. One's the area of a circle, the other is the circumference, right? What do you think happens if we integrate the circumference of a circle? We get the area, right? It puts it back together. It's like it tells us to go through and add up all these concentric circles all the way through and get the area of a circle. What's the derivative of ddr of 4/3 pi r cubed? And what is that? Surface area, yeah. 4/3 pi r cubed, volume of a sphere, surface area of a sphere. All right. Well, that's pretty cool. That's kind of neat. You have to have a little appreciation for that one. And the same thing. So one breaks it into shells, and if you integrate, you're essentially adding up all those concentric shells inside your sphere and getting the total volume. All right. Don't need to leave that on there. Any questions so far? No? Okay, so let's take a look at some examples here. So use the fundamental theorem to find dy dx. So if we look at this one, we're going from A to B. We want to find dy dx. That's going to be d dx of the integral from A to x of t cubed plus 1 dt. A is a fixed point. So by this fundamental theorem, what's this going to equal? Yeah. It's the derivative of an integral, right? Because if you went through and did the antiderivative of this, you'd get a function of x plus some constant that had a's in it, right? And then when you take the derivative of that, our function that we just integrated to the, now we're taking the derivative of it, that gives us back x cubed plus 3 from the x. And then the part that had a's in it goes to 0, right? Right? So we just lose that a part. It's just x cubed plus 1. All right, want to try this next one? So let's take a look here. We've got y equals the integral from x to 5 of 3t sine of t dt. So dy dx is the derivative of this, right? But they're flip-flopped. So what can I do? Well, yeah, you're just jumping ahead there. But yeah, we can reverse. Once we learn how to actually go through and do these by hand, you'll see that that bottom one, it would have been a minus, and then the constant would have been out front, and it would have resulted in the same thing. But you can also use those rules. D dx of negative 5 to x 3t sine t dt, like that. So this is just going to be negative 3x sine x, no dt. What am I doing? There you go. See that? So we just had that negative on there. All right, take a look at the next one. We're going from 1 up to there. What do we think here? We're going from 1 to x squared. Pretty good, yes. Pretty good. dy dx is d dx integral 1 to x squared cosine t dt, right? But when we take that derivative, right, of whatever there is in there, when we put that x squared in there, we're going to have some sort of chain rule, right? So we're going to have something like a cosine of x squared times whatever it is inside our function, thing like this prime because of chain rule. So we end up with cosine x squared times x squared prime, right? You need a derivative, so you just end up with 2x cosine x squared because chain rule. All right. What about this next one? There you go. You got this down, huh? So we can first swap it. Y equals that negative. And so from 4 to 1 plus 3x squared, 1 over 2 plus e to the t dt. And then we can do dy dx, dx, and I'll put the negative out front there, of 4 to 1 plus 3x squared, 1 over 2 plus e to the t dt. And then we've got negative 1 over 2 plus e to the 1 plus 3x squared, because I substitute that in for the t, times my 1 plus 3x squared, and then take the derivative of it. Chain rule again, right? And then this just becomes negative 6x over 2 plus e to the 1 plus 3x squared. So you got to do chain rule for it. Okay? Because once you plug that in, it becomes something you have to do the derivative outer and derivative inner, right? So not too big a deal there. All right. Okay, any questions? Everybody able to access the notes when they back up online? Okay, good. All right, fundamental theorem of calculus part 2. Here we go. This is the evaluation part. So here, if f is continuous on AB, and our big F is an antiderivative of f on a b, then the integral a to b of f of x dx equals f of b minus f of a. So all you have to do is find the antiderivative, plug in the upper limit, and then subtract off when you plug in the lower limit. Right? Couldn't be easier, right? Except this gets to be way harder than derivatives. Derivatives are easy compared to integrals. Integrals can become very difficult. Way more difficult even than what you'll see in this class. Okay? Like, there are entire textbooks that are just filled with nothing but integrals. They're called integral tables, and they're just filled with tons of them because doing them by hand every time it just gets to be crazy, and it just can't be done. So when someone finds one, they throw it in the book. So, okay. All right. This theorem allows us to calculate the derivative. This theorem allows us to calculate the definite integral by doing only two things. One, find an antiderivative. F. Notice it's an antiderivative, not the antiderivative. That'll be important when we do indefinite integrals. Okay. And two, calculate the number f of b minus f of a. That's it. Just do those two things. You're good to go. So here are some different notations you might see for this. So actually here, the fundamental theorem of calculus allows us to view integration and differentiations. This is what I was just talking about as inverses of each other, which is what so much of math is about, right? To start solving things is all about finding inverses. So now we've got it. So let's take a look at this. Some notation, f of b minus f of a. Some ways you might see this. You might see this as f of x evaluated, sometimes with a bracket like this from a to b. Sometimes it's written like a bracket. That wasn't a very good bracket. A bracket f of x a to b. Sometimes it's written f of x like this, and you'd say evaluated from x equals a to x equals b. And then the way I tend to write it is just evaluated from a to b like that, that last one. But all those four things there, they're all saying the same thing. It's just, I guess, personal taste. But you should recognize it because as you go to different textbooks and different sources, you know, different people will write it different ways. Another thing that's kind of interesting is we write integrals like this. We write them like integral a to b of f of x dx. But in Europe, I've seen a lot of them. I don't remember if it's everywhere there, but a lot of them in Europe, they actually write the same exact thing. They write it like, and the first time I saw this, I remember having trouble because I thought it was telling me the integral of 1 times f of x. You know, but that's the way they write them. They put the dx, the integral with the dx first. So it's like an operator. We sandwich it inside the operator, and they're putting the operator all together and saying it's acting on f of x kind of a thing. But anyway, any questions? Doing okay? Only 3 more pages. We got this, right? Evaluate the integral. So let's take a look at this one. What can we do here? What's the first thing we have to do? Find the antiderivatives, right? Which you started in Calc 1, right? So here we can do it on each one individually. And so we'll look at this and we say, what's the antiderivative of x squared? X cubed over 3, right? X cubed over 3. And then what's the antiderivative of 2x? Yep. So it's like 2 times x squared over 2, right? And those 2's are going to cancel. And if you take the derivative of x squared, you get 2x, right? So we're just working backwards. So I guess previously you pulled the exponent down and multiplied by the exponent and then reduced it by 1. Now you're increasing the exponent by 1 and then dividing by that new exponent, right? So then this becomes what? Plus 3x. And then we're evaluating this from -1 to 1. So we start with 1 cubed over 3 minus 1 squared plus 3 times 1 minus, right? And we can do this whole thing. This is -1 cubed over 3 minus -1 squared plus 3 times -1. And then this will become 1/3 minus 1, minus 1 plus 3 minus, so it's minus -1/3 because -1 cubed is -1. So this becomes plus 1/3. And then -1 squared is +1, minus it again, so then a plus 1. And then that's -3, -3, that's plus 3, right? And so we have -1 plus 1. We have a third plus a third. That's 2/3. And then we have a 3 plus 3. That's a 6. And then, you know, you make that 18/3. So then that's, yeah.
Why would it be plus 3 because it's times a -1?
Yes, but then it's minus. It's 3 times -1, it makes it -3, and then minus that. Minus -3. So this is just 20/3, right? I didn't redo it. Okay. So let me look. I'm going to leave some of these for you to try here in a minute. So we knew the derivative of what is cosine? Sine. So there's that one. Square root of x is just x to the 1/2, right? For part C there. So I'm going to leave you B and C to do, but let's take a look at D. All right. So when we look at D, so this one, you know, derivative of sine of x is cosine x. That's your little hint there. That should do that for you. And of course here, our hint is square root of x equals x to the 1/2. So I'm going to leave those for you to try. And they're both pretty simple answers. So let's take a look at this one. What we need to figure out here is the derivative of what equals a 1/x, right? I know we have that x plus 1, but so we're going to have some sort of natural log, but the natural log of what? There you go. Just a little hint for you. I know we're going to keep with it. When you get going, if you go to grad school or something for math, that absolute value part, don't include it. I think that's done mostly at this level because you're not doing complex calculus, but it actually doesn't need the absolute value. So anyway, I think that's just this part of making it real. But yeah, the absolute value of x plus 1. Oops, I put up. Yeah, that's what we need right there. Therefore, our integral becomes the natural log of the absolute value of x plus 1 evaluated from 0 to 1. Okay, and you can plug those in. I'll leave that there for you. Okay. Written one down here to also look at with you. I might just give it to you as something to look at and try to figure out and find here. But let's do like a D. Let's do an E. And I want you to try this one. Integral from 1 to 2, natural log of x over x dx. So do that same thing. You need to find d dx f of x equals ln an x over x. And just try a few little guesses and checks and see if you can come up with it. All right, this should turn out to be not too complicated. All right, see if you can figure that out. Okay. Don't tell. Don't tell. Wait, are you telling the answer? No, don't tell the answer. Let everybody go try it. I'm throwing this extra one on there. I have it written down here. We'll go over it. We'll go over it tomorrow. All right. And then last thing here, pretty simple idea here. If you want to do the total area where you're not counting the parts below the axis as negative, then you simply break it up and do the integral where, you know, in sections where it crosses the x-axis. So if you look at this one, you would break this into two sections. One would be from 0 to pi, and the other would be pi to 2 pi, and you'd take the absolute value of both. Because otherwise, when you integrate this area down here, it's going to be negative. So that's the basic idea there. Just separate them and divide it up, and then integrate each section, and then add them up. So let's try this one right here. Y equals the sine of x from 0 to 2 pi. Now we see this in the picture already, that we need to do this from 0 to pi and then pi to 2 pi. So our total area is going to be the absolute value from 0 to pi of sine of x dx, right, plus the absolute value from pi to 2 pi sine of x dx. See that? And that's pretty much going to be it. So the derivative of what gives us sine? Negative cosine. So this will become the absolute value of negative cosine of x dx. And this one we're evaluating from 0 to pi, plus the absolute value of negative cosine of x dx from pi to 2 pi, just like that. And then you just start plugging them in. The cosine, this becomes absolute value of negative cosine of pi minus negative cosine of 0 plus absolute value of negative cosine of 2 pi minus negative cosine of pi. Absolute value. Cosine of pi is? Cosine of pi is? Cosine of pi is? Yes, -1. All right, here's our unit circle. Here we're at 0, pi over 2, pi, 3 pi over 2, and then 2 pi, right? Going around like that. So we're doing cosine of pi, that's right here. That's the point -1, 0, so it's -1. So this is negative of -1 minus the cosine of 0. That's right here at the point 1, 0, right? So this is minus -1, just like that. And then absolute value plus absolute value of negative cosine of 2 pi. Well, cosine of 2 pi is also 1, so this is -1. All right, and then we have minus negative cosine, so we can make that a plus, right? I guess I could have done that before. So the cosine of pi is -1, so this is like plus -1. And so then we end up with negative of -1 plus -1 minus 1 plus, right? So that's 1 plus 1, 2. Over here we have -1 plus -1, that's -2. That's 2 plus 2, that's 4. What would it have been if we hadn't done the total? What if we had just integrated from 0 to 2 pi? We would have gotten 0. Okay. I'm going to leave that next one for you to try. You've got a picture there already showing how it's broken up, because we have a few minutes left in class. So I want y'all to hang around and work on these. And that's pretty much it for this section. Any questions from anything we just went over? No? All right.